Okay, let's do a really quick recap of where we ended up with stat-mech, basically definitions and variables. So we have the energy. This is the energy of a particle based on some properties. And through this we have energy states. Right, and a particular energy state is one where we have, in the case of particle in a box, there is the Lx, Ly, and Lz parameters. That's some unique configuration of Lx, Ly, Lz, right? A unique set of conditions for that particular state. But we also have energy levels, right? And the energy level is what is the energy of that state, right? And there may be several energy states that all have the same energy level. We also wrote what the probability, in this case the P of I corresponds to state I with energy equal to E alpha, right? So this is a unique state. So a unique particular, having a particle in a very specific configuration with a very specific energy. What is the probability that we're going to find it in that condition? And to evaluate that, we had a Boltzmann factor scaling the energy. So the higher the energy goes, the lower the probability is that you're going to find the particle in that state. And then you have to normalize this by all of the possible configurations of the system. So we just add up all of the possible configurations, possible energy states. And we call this denominator the partition function. In this case, the uppercase Q is specifically the canonical partition function. And we call this the NV beta or NVT, meaning that our system is at a constant temperature with impermeable walls and fixed rigid walls at the same constant volume. So it should be a one-to-one analogy to when we work through thermodynamic calculations at constant, T, U, and N, or T, V, and N rather, right? So a lot of the stuff that we do as chemies is at constant temperature and pressure. So if we wanted to do a calculation in stat-mech at constant temperature and pressure, we wouldn't want to use the canonical partition function. We would want to use a different partition function. And each of those new partition functions have a new derivation approach. So the equations are all going to be slightly different. What we're focusing on is really the easiest, most straightforward one, which is the canonical. But then there's the grand canonical, the microcanonical, the isobaric canonical. There's all these different partition functions that all have slightly different relationships. Okay. Recall then that beta is 1 over kBT. So what we're going to be introducing today is that Q is the partition function for just a single particle, whereas the capital Q is typically reserved for a collection of particles. So right now, we've only been dealing with one particle, so little q and big Q are interchangeable. And then lastly, the internal energy, U, we define that as the average energy. And so it is a weighted average of the energy of a particular state multiplied by the probability of being in that particular state. And we can relate that to the partition function with a little bit of clever calculus. So as it turns out, the math that we work through reveal that if we have the partition function, which is a weighted summation of all of the possible configurations of the system, that tells us what our internal energy is. We can also expand it to tell us what the pressure is, the entropy. Everything comes from the partition function. So what we're going to try and get to by the end of the day, hopefully we make it, is our goal is calculate Q for an ideal gas. And we all know what the result should be, right? What's the internal energy of an ideal gas? 3/2 N kBT. Right? That's the goal. That's what we're trying to get to. But we all know the outcome of that. Right? C sub V for an ideal gas, 3/2 kBT. Right? So that's what we're trying to get to. But we have to meet there not from some observation of actually heating up a monatomic ideal gas, but actually from the fundamentals of how we think that these molecules should behave. So what we need is we need a partition function for one molecule, in this case, or particle, and then we need to scale it to n particles. We're going to calculate the Q, and then calculate the internal energy. So there's a few bookkeeping items that we have to take care of before we can accomplish all this task, but that's our plan to work through today. So the first thing we're going to talk about is a simplification to make our math a little bit easier, and that's called multiple energy modes. So in the case of a monatomic gas, we only have translational energy if, of course, we neglect the electronic properties of the system, which is generally a good assumption. Right? The energy involved with taking an electron to a ground state from an elevated to an elevated state is actually much, much more energy than it takes to actually just push the particle in a particular direction. So for a monatomic gas, it can have a velocity in the x, a velocity in the y, and the velocity in a z. And these all turn out to be symmetric, right? It doesn't matter how I define x, y, and z. And certainly the gas molecule doesn't care what's x, y, and z either. If we have a diatomic gas, we have translation, right? That molecule could be moving in each of those three directions. We have rotation, right? The molecule can rotate. And we actually can also have vibration. As it turns out, the vibrational mode is a fairly high energy mode as well. That doesn't really get activated until you're at a reasonably high elevated temperature. Translation and rotation are very easy to do. So let's say we have a diatomic particle with 3 translational and 3 rotational modes. Right, so this particle can have, let's say, a velocity of 1, 2, or 3. Let's say it can have a rotation of 1, 2, and 3. And these could correspond to the frequencies or the velocities, whatever the case is, we don't need to know how to come up with that energy level, right? We're just saying it's got 3 different energy states, right? And then after the fact, we can come up with the math to figure out, okay, how do we translate the particle properties to an energy of 1 in the translation or energy of 2 in the translation? So if we are to write out the partition function, what we have to do is we're adding up all of the states. So if I have 3 translational modes and 3 rotational modes, how many total possible configurations do I have for the system? 9, right? So we have 9 individual modes. So if I were to write out my partition function for the single particle, Q, I have to add up the scaled, all of the scaled energy states. So in this case, it'll be exp, I'll call it epsilon T1 plus epsilon R1 for the translational mode 1 and rotational mode 1, right? That's one of my 9 states, plus exp. I'm not going to write all of these out because you'll see the pattern very quickly. T1 plus R1, right? And notice that this right here, that's like the energy level of that particular state, right? That particle state is in translational mode 1 and rotational mode 1. The next one over here, this one is in translational mode 1, rotational mode 2. And of course, we can just keep, oh, sorry, there's the 2. There we go. And we can repeat this down and repeat this across, and eventually our last entry here, epsilon T3 plus epsilon R3. Right? So we should have 9 total entries into our partition function for a single particle. Now with with exponent properties, right, we can write this expression here. We can simplify it down a little bit. So we can write this as exp minus beta epsilon T1 times by exp minus beta epsilon R1. Right, just an exponent property. If I'm adding things together in an exponent, it's the same thing as multiplying them outside of the exponent. Good? So if we apply this logic throughout, we can break down this partition function into a much simpler form. We can write it now as e to the minus beta epsilon T1 plus e minus beta epsilon T2 plus e minus beta epsilon T3 times by e to the minus beta R1, epsilon R1, basically just factoring and simplifying the system. And what we're going to do, this is equal here, is we're going to call this first term the partition function for the translational energy modes. And this one here is going to be the partition function for the rotational energy modes of the system. So that way we will write our single particle partition function. In this case, we made a very small, simplified system of 3 translational modes and 3 rotational modes, when in reality we have an infinite number of rotational modes and translational modes. But we can write this as the product of the 2 individual partition functions. So we call these independent modes. Now this is a simplification that we can use on dilute gas systems. But let's say, for example, we have a dense, high molecular weight material. Let's just say something simple, like a heptane, for example. So that's 1, 2, 3, 4, 5, 6, 7. So if we were to take a molecule like heptane, from a classical thermodynamics perspective, heptane's a pretty simple molecule, right? We could probably get one of the cubic equations of state to predict its vapor-liquid equilibrium. Not too bad, I bet, right? Simple hydrocarbon, weakly interacting. But if we look at it from stat mech, we have vibrations, and this is, of course, neglecting all the hydrogens, right? So we have vibrations between all the CH bonds, vibrations between all the CC bonds. We have vibrations, angular vibrations like this. Same thing also with the hydrogens as well. You can have rotations of whole functional groups. Now, if I was doing a gas phase dilute system heptane calculation, you know what? I could probably assume that all these energy modes are independent, right? Because if it's a dilute gas, the heptane is just zipping around. Yeah, I'm sure it can rotate and bend and flex, and it doesn't really impact itself, right? But now if I were to take this and put it into a liquid, well, certainly, if I had some large vibrational mode going on in my system with another heptane right nearby, that might impact how it's going to be rotating and moving. In that case, you may not be able to assume that you have independent energy modes. But the simplification here is what we've done is we've taken this complex combined problem of saying, oh, it can be in translational mode 1 and rotational mode 1, and broken it down to saying, you know what, I'm only going to do one calculation based on translation, and I'm only going to do one calculation based on rotation. And these are independent multiple energy modes. It's a simplification that we're going to use when we apply to the ideal gas. Okay, any questions on this? Now, again, these are all modeling approximations, right? We've neglected quantum mechanics. We've said everything's independent. Right? Again, these are all just different strategies and pathways to come up with new theoretical derivations and things like that, right? So they're not 100% accurate, but they're good enough in some circumstances. And again, these are all ideal gas calculations. Okay, so the next step is a real gas is not just one particle zipping around in a box. It's a lot of particles zipping around in a box. Right? So what we're trying to go from here is Q, the partition function of a single particle, all the way up to the big Q for a collection. So this is for a single, and this is for a collection. Now, of course, if we have only one particle in our system, then big Q is equal to little q, because the system is just that one simple particle. So how we do this is if we assume, right, that every single particle behaves completely independently. We could say then that Q is equal to Q1 times Q2 times Q3 and so on and so forth, right? Because if everything's completely independent, right, I have some number of configurations that particle 1 can be in, right? And boom, I've locked it into state 7,258, right? Particle 2 can be in just as many configurations, and the two of them are not communicating whatsoever. So I have the total number of configurations of particle 1, total number of configurations of particle 2, times them together, that's how many configurations for the combined system. So this would work out to be Q to the n power for the n number of particles. Yes?
This is assuming for ideal gas?
This would be for, well, not any non-interacting system. So in that case, yeah, ideal gas would be appropriate.
So I actually have a question regarding this. So if, like, so our Q, our partition for the question is going to be really massive, because I mean, if we have like 9 different states, you know, and then you said we're going to be doing what, like 1,000 species, so 9 to the power of 1,000?
Yep.
Okay,
So there's some approximations that we use to help simplify the math. But it's funny how it all kind of works out not that badly. The thing is, so one of the things to keep in mind is that the energy states are really, really close together, right? Because when we looked at the particle in the box, there was that Planck's constant, right? I think it was Planck's constant squared, which is 10 to the minus 34 squared, which is then what, 10 to the minus 68? So you can get pretty close to infinity.
63 to 6 times 6.
Right, so there's a tremendous number of states. And so when you have a lot of particles, as it turns out, they don't overlap in the same state that often. And the math all just kind of works itself out nicely. So this approach right here is neglecting one very important fact. Right? In the case of the previous example here, right, where we have the two independent energy modes, I can tell the difference between a particle moving versus a particle rotating, right? In theory, you can come up with some sort of a spectroscopic technique or visualization technique to see what the difference between the two of them is. But in this case here, when I combine particle 1, particle 2, particle 3, I've said that I know what particle 1, 2, and 3 are. We've neglected the indistinguishability of molecules. So in reality, this approach is not valid. What you actually have to have is Q is equal to 1 over n factorial Q to the n. This n factorial is called the indistinguishability factor. Ability. And this can be sort of thought of conceptually is if we're trying to put n identical balls or particles into a series of boxes, right? The boxes are going to represent the energy states. The balls are going to represent the molecules that are indistinguishable, right? So if I have three balls that I'm putting into three boxes. I have bin 1, bin 2, bin 3. These could correspond to different energy states. In this particular one, I could put either 3, 2, or 1 into that bin. And I can put 2 or 1 into that bin, 1 into this bin. And we can see that we have 3 times 2 times 1, which is equal to 3 factorial. In this case, generalizing it, that is n factorial. That is our indistinguishability factor. I can't tell my molecules apart, but I can categorize them into energy levels or energy states. So now we have all of the tools that we need in order to calculate the partition function for a collection of particles. So the last thing that we need is now a model for our particles. Right? If we have a model to calculate the energy states or the energy levels, then all we need to do is sum them all up, calculate our partition function, calculate our internal energy. So we're simplifying the calculations down to a much more, coherent, tangible way. Right? What are the rules that I think a particle in a box has to behave by? So we're going to go back to the quantum mechanical description of a particle in a box. Oh, sorry, one thing before that. If we have distinguishable particles, so we have Q of n1, n2, ... at constant V and beta, right? So if this is a mixture of, let's say, helium and neon, right? Helium and neon are distinguishable. So in that case, our partition function for a collection of particles will be the product sum of I equals 1, Qi Ni over Ni factorial. So in this case here, all we're doing is taking this function here and saying for every particle type I have that partition function times by the partition function of the next one. So in this case here, 1 and 2 are distinguishable. Right, so there'd be two different types of gas molecules, right? Because obviously helium and neon have different atomic weights, different electronic structures, different spectra, so we can differentiate between the two of them. But any individual helium atom cannot be distinguished from any other individual helium atom because of the Heisenberg uncertainty principle. So it just affects the combinatorial statistics, right? Okay. So now what we need is the energy of a particle. Once we have the energy of a particle, we can calculate the partition function for a single particle. Then we can calculate the partition function for a collection of particles. And then we can calculate the internal energy, the pressure, the heat capacity, any other chemical property that we want. So for right now, our pathway from the microscopic stat mech state to the macroscopic state is through the internal energy. But we're going to be developing other relationships very shortly. For right now, the internal energy is our connection between the two. So we're going to use particle in a box. All right, so we're going to borrow from quantum mechanics the energy of a particle in a box is a function of the quantum numbers Lx, Ly, Lz. We have Planck's constant, mass of the particle, volume of the box, and the three different integer numbers, Lx, Ly, and Lz. Which if we were to translate this to sort of a macroscopic scale, these would correspond to maybe velocity x, velocity y, velocity z. But at the quantum scale, you can't have continuous descriptors, so these have to be discrete integers. So for simplification, I'm just going to define this A as all of the gunk in front, 8mv to the 2/3. So that we can simplify our epsilon to A just makes the math a little bit less painful. Okay, so now we have a model, right, of how the energy of one particle should behave. So we can write out the partition function. The partition function is just adding up all of the energies for all the possible configurations of all the possible states. So what we have then is a triple summation. Because in our energy function, right, I can't control Planck's constant, I can't control the mass of the particle, and I'm in the canonical partition function, so the volume of my box is fixed. So the only thing that I can change to control the state of the particle is Lx, Ly, and Lz. So I have to sum up over every possible Lx, every possible Ly, and every possible Lz. And I scale that by theta, which is my reservoir property, right? All we're doing is following along what we've done so far, is just scaling all the possible states to get our partition function. And so this term here, right, I just put this as a function, right, where epsilon is a function of these three variables, as opposed to writing out the whole function. But we can simplify this. There's a lot of ways that we can simplify this. One, Lx, Ly, and Lz, that looks pretty symmetric. So we can say that these are independent energy modes. So then we can rewrite our partition function as Qx, Qy, and Qz, where, for example, Qz is equal to the summation of L, Z, e to the minus beta, A, epsilon, L, Z squared. And the same thing applies for Ly and for Lx. So now we only have to evaluate this infinite summation for one of the three directions of translation, and then we just cube it, and that simplifies our math a little bit. Okay, I don't know about you guys, but I am not comfortable with infinite summations. Right? They are not pleasant to deal with. So what is similar mathematically that's a lot more fun to work with than a summation? An integral. So the question is, can we turn this summation into an integral? Under what criteria do we think that's an acceptable approximation? So LZ is going to go from 0 to infinity. Right? So under what conditions can I substitute a summation for an integral? Energy levels are small. If the steps between the summation states are very, very small, one might say differentially small, then we can just add up thin slices as if this were a continuous function. So this is a discrete summation, but we're going to approximate it as a continuous function. And so what we want to do now is just double check to make sure that that's a reasonable approach. So if we want to replace, now let's go to the next slide here. So we want to replace the summation with a continuous integral, right? Going from 0 to infinity as opposed to going from 0 to infinity. Much, much easier to use calculus than it is to tinker around with an infinite summation. So is this okay? The answer we know is yes, because that's what we're going to do. But if we look at the actual parameter, so if we look at this A parameter, which is the prefactor in the energy of our model, which is the particle in a box, A is on the order of 10 to the minus 33 units called ergs, which 1 erg is equal to 10 to the minus 7 joules. Just a small unit that's really commonly used in these types of calculations. And this is, of course, for a mass of approximately one atom, which is approximately 10 to the minus 22 grams, and a volume of 1 liter. So if we have one particle and a 1 liter volume of box, this is what our A turns out to be. And of course, remember, A was equal to h squared over 8mv to the 2/3 power. So then our beta, under ambient conditions, something that, again, is reasonable to work with, is about 10 to the 16th ergs per Kelvin. It's equal to about 10 to the 23 joules per Kelvin, which is 10 to the minus 23, which is equal to 1 over kVt, give or take. So if we were to look at one of our partition functions for the, let's say, the x translational mode, this quantity of beta times alpha is about 10 to the minus 17. Whereas Lx, Ly, and Lz are integer values. 0, 1, 2, 3, all the way up to infinity. So my summation is in steps of 10 to the minus 17. So that's probably totally sufficient to approximate that as continuous. So now we have to evaluate our partition function. And this is where things start to get a little bit kind of weird and abstract, right? The partition function began its origin as adding up all of the possible energy states of the system in a summation. And then somehow we're turning this into a continuous function and then somehow that continuous function is just going to spit out a number. It's just going to be a number, which is a little bit weird, but it all actually works out well. So we're going to say that Qx is equal to summation over the Lx and we are going to then say this is exactly equivalent as integrating from 0 to infinity. So actually I'm going to call this A prime. Where A prime is just equal to A times beta, just to make things a little bit simpler for the integration. Okay, off the top of your heads, what is this integral?
Square root pi over a over square root pi, or square root a over square root pi, something like that.
You're kind of close. It's actually a custom special function. I don't think it has a direct analytical, but it's called the error function. So the solution to this here is, so if we look at the integral of 0 to infinity exp of minus a prime x squared is equal to and this is called the error function. So it's something that just pops up quite a lot. And if you were to plot out the error function, this is 1, this is minus 1. It looks like this. So this should cross 0. So at 0 it is 0, and at infinity it is 1. So that tells us that our partition function for x, which is the integral from 0 to infinity, very conveniently works out to be nice and simple. So then Qx, if we unsubstitute everything back in, pi over 4a prime, 2 times the mass times by pi times by the volume to 2/3 divided by beta and Planck's constant squared. The single particle partition function is the same thing for x, y, and z directions. And we get a nice, relatively nice looking function. And we have a single particle partition function. The next step, partition function for a collection of particles. Is we just have to evaluate this expression. So we're very close. Give everyone a second to write that down. So let's write out the partition function for a collection of particles, which is the partition function that we just derived for indistinguishable particles. But let's say, for example, we were to have a binary mixture. Our partition function would look a little bit different, right? Because you could distinguish between particles of type A and particles of type B. But since it's only one type of gas, they're all indistinguishable. So we're starting to see some numbers popping up that kind of look like the answer we're expecting to get. So if we evaluate the natural log of Q, which is what we're going to have to differentiate with respect to beta, we can simplify this expression down quite a bit. Now we'll calculate our internal energy, which is minus the negative natural log of our partition function with respect to beta, which of course, remember, beta is a form of writing the temperature. So we want to see how does the total number of energy states change as I change the temperature, which is effectively what we're asking here for what the internal energy is. So the far right term, there is no dependence on beta for that. That's all constants in our system. So that just goes away. Our first term, when we take the derivative, is just minus 1 over beta. So when we put it all together, U is equal to 3/2 n over beta, 3/2 n kBT. C sub v is, of course, du dt at constant v, 3/2 n kB. So we went all the way from quantum mechanical description of a single particle in a 3D box, all the way up to a prediction of what the heat capacity of that particle should be. So for an ideal monatomic gas in a constant volume box, right, we already knew that the heat capacity was 3/2 R. Right? So if I say that N is equal to NA, Avogadro's number, that means that NA times by KB is equal to what? R. So in that case, C sub V is equal to 3/2 R. So what we're going to be doing in the future is we're going to take the same partition function and we're going to figure out, well, how does the pressure change, or how does the entropy change? And then we're going to talk about new partition functions and more complex systems, right? Obviously, for a diatomic molecule, not only do we have to keep track of the translational modes, we have to keep track of the rotational modes, we have to keep track of the vibrational modes. And so that'll give us a slightly different partition function. So when we take the derivative of it, it gives us a different result for the C sub V or C sub D. But what we're going to be doing now moving forward is we're going to be tweaking the model, tweaking the partition functions or the ensembles that we're working in, right? We're not necessarily always going to be working in the canonical ensemble. Maybe it's the grand canonical ensemble or the micro-canonical ensemble. And it's not necessarily always going to be a monatomic non-interacting gas. Maybe it's a monatomic interacting gas. Or maybe it's a non-interacting diatomic gas. But this gives us fully predictive power. Right? All we need to do is come up with a model for how a molecule stores its energy and moves around the system. And with StatMech, we can then predict what its heat capacity should be. Whereas from classical thermo, there was absolutely no way to know what the heat capacity was other than by experimental observation. Right? And so that's something that we've just taken as a fact, that when we want to calculate a state change, we just know that we have to integrate either C sub V or integrate C sub P, the heat capacities. Right? But now with StatMech, we have a predictive tool. So we've broken down the debate now, not in terms of, okay, well, why does fluid A behave a certain way and fluid B behave a certain way? Well, let's just measure it in the lab and not worry about it. That's the classical thermo approach. Classical thermo does not have predictive powers unless you give it experimental data input. StatMech has predictive powers, and it breaks down the question into, how do I think the physics of a single molecule change based on changing its properties? Or how do I think that molecules of type A interact with molecules of type B? Can I put them into a dense fluid and then predict how I think their phase behavior should be, or their heat of mixing, or their heat of vaporization? Right, so this lays out the groundwork to not talk about continuous fluids as these magical goos, right? Because classical thermo came before we knew what an atom looked like, was, or behaved, or how big it was. So we really didn't know how a particular fluid behaved. So we just had to measure it. But now we've got a system where we've broken it down, and we can talk about the specific subtle details of how a single molecule will behave, and then translate that into a macroscopic calculation of, well, what is really its internal energy? How much energy does it take to heat up? How much energy does it take to vaporize it? Right? We're not going to be able to answer all of those questions in class, but at least we're going to lay out the terminology and go through a couple of the simple classic calculations so that when you do pick up a paper on StatMech or molecular simulations, that these terminologies don't seem totally out of place. Right? Because this terminology of partition functions and is it ergodic, is it non-ergodic? These are all terms that you'll see very, very frequently if you read the literature on molecular properties and molecular behaviors. But unfortunately, we don't have enough time to go through all the long details, but it's a fairly advanced field. Okay, any questions before we break for the weekend? Yes?
Can we get back to when you're approximating beta 10 to the 16?
Yes, this one here?
Yeah, so we're getting confused because one erg is 10 to the minus 7 joules, and so it's just the conversion from 10 to the 16 erg per Kelvin to like 10 to the 9 joules.
I would have to go, let's see, so A, let's see. I may have to take this one offline. I might not be able to rework it out in my head right here. So beta's 10 to the 16. So we're saying that, so beta 10. Okay, so if we do it in terms of ergs, what's minus 33 plus 16? What does that work out to be? Is that 17?
Yeah.
But yeah, we can go through this. I won't be able to reproduce it right now off the top of my head. But I think if we keep it all in ergs, so is the concern going from here to there?
Yeah, so it's going from 10 to the 16 erg per Kelvin to 10 to the 26 per Kelvin. If one erg is 10 to the minus 7.
Yeah, I might have messed that part up. But I think this part is okay. The BA is 10 to the minus 17. That would be in units of ergs. But yeah, let me double check that real quick, and then I can answer that question. But ultimately, the assumption that we can approximate this as continuous is okay. And if not, it makes our life very, very difficult. But there are some systems where you can't necessarily assume that it's a continuous function. So for example, electronic and vibrational energy states you cannot approximate as a continuous function, because the energy levels involved of transforming an electron from the ground energy state to a higher energy state is a big step. So for some partition functions, you do have to keep it as a summation. But in these particular ones for translation and rotation, you can approximate it as continuous. Okay. Yes?
How do ergs relate to electron volts? So you know,
Oh, there is a straight conversion. An EV is a unit of energy as well.
is it like a lot more ergs or a lot fewer?
I don't typically work in EVs. I know a lot of people use it a lot, but as it turns out, I'm not very good at What's that?
It's smaller than erg? Okay.
That's one EV? Yeah, because I know it's a pretty small unit, but I don't do a lot of electrochemistry or anything like that, so I don't typically work in terms of EVs. With X-rays, a lot of times they like to report, so I do X-ray scattering a lot, and they like to report X-ray energies in EVs. So I know that the X-rays that I use are, 8 keV is a typical energy of X-ray that we scatter with, but I don't actually care about the energy. I always just translate it to wavelength. So I know the translation between EVs and the wavelength of the photon, but I don't actually ever translate EVs to a macroscopic energy. But we have our answer. Yeah, EV is much, much smaller. All right, good questions. Thank you.